In this part of the video, I will talk about how to sketch the graph of a rational function. So here I provide a guideline for graphing rational functions. Again, in general, we're going to let an f of x equals n of x divided by d of x, where n of x and d of x are polynomials, and d of x, the bottom polynomial, is not going to be 0. So if this is the case, then what we're going to do before getting graphing is that we're going to simplify the function. In other words, factor the top and then factor the bottom and then try to cross out if there's any similar factor. Also try to simplify if there's like a common leading coefficient or any kind of multiplicity. Second thing we're going to do is we're going to find and plot the y-intercept by evaluating f of 0. So that's the general rule. When we find y-intercepts, we know that x must be 0. So we replace x equals 0 into the function and then find the value for that. Next thing we're going to do is we're going to find the zeros of the numerator by solving the equation n of x equals 0. So that's going to give us the x-intercepts. And then next thing we're going to do is we're going to find the zeros of the denominator. So we look at the bottom, d of x equals 0, and then sketch, because this is going to be the x values that makes the bottom is going to be our vertical asymptotes. That's why it's important. We're going to find and sketch the horizontal asymptotes. So we just learned about the rule in the other video where we need to use the rule for finding horizontal asymptotes. Plot at least one point between and 1 point beyond each x-intercept and a vertical asymptote. I'm going to show that pretty soon. And then we're going to use smooth curves to complete the graph between and beyond the vertical asymptotes. So those are the general guidelines to be able to graph rational functions by hand. Previously, I introduced the idea of using test intervals. So here we can actually use test intervals as well. To do this, we use the fact that a rational function can change signs only at its zeros and its undefined values. So previously with polynomials, when we were doing test intervals, we were only including zeros, but with rational functions, because of this nature of these functions, you also need to include the undefined values. In other words, the values that makes the bottom 0 should also be included for your test intervals. And then we're going to say between two consecutive zeros of the numerator and the denominator, a rational must be entirely positive or entirely negative. So then I'm going to jump right into the example here. Sketch the graph of g of x equals 3 over x minus 2 and state its domain. So we first of all start with the y-intercept. So we're going to take a look at when x is 0, what's y value. So you place 0. What you will find is g of 0 is just negative 3 over 2. We're going to find x-intercept. So for that, we need to take a look at what makes 3 over x minus 2 equals 0. So we're going to ask this question. So you guys realize because x is at the bottom and there's 3 at the top, this is not possible. The reason being is that when you do cross multiplication, you're going to realize you can write 0 as 0 over 1. You're going to realize 3 times 1 equals 0 times x minus 2. And you're going to always get 3 equals 0, but that's not true. So what that means is because there is no x to the top, there is nothing to solve for. For that reason, there's not going to be any x-intercept. So this rational is not going to pass through the x-axis. That's what it means. We're going to take a look at the vertical asymptote. Look at the bottom, make the bottom 0, so x minus 2 equals 0. Solve this for x, you get x equals 2. So that must be the vertical asymptote. For the horizontal asymptote, you guys realize you need to apply the rule. So look at the degree of the top. So this guy has 3. So the way we find the degree of a constant polynomial is we think of it as something like 3 times x to the 0. Because what this equal to, it's actually equal to 3 times anything x, like anything raised by 0 is always 1. So it's just 3 times 1, which is 3. So think of it that way. And then what's the degree of this? Look at the x. X has the 0 at the top, so n is 0. The degree of this guy is just x to the 1, which is m equals 1. So look at the bottom degree is bigger than the top degree. In those situations, we're always going to say y equals 0 is the horizontal asymptote, or x-axis is going to be the horizontal asymptote of this rational. So now we do this idea of test intervals. So what I'm going to use is that because I don't have, so let's go back. Because I don't have any zeros, there's no x coming from there because the top is never going to be solvable. Like there's no, so this one is basically zeros. So this function doesn't have any zeros because the top doesn't have any x. The only thing we're going to include in the table is going to be the vertical asymptote, which is x equals 2. So we include that value. So we use 2 to come up with test intervals. So we say negative infinity to 2 and then 2 to infinity. So we only can come up with 2 intervals. And then we're going to pick some representative x value or random x value, evaluate the function as we previously did, find the sign, and then pick any random point on the graph just to make sure how the function behaves. So by plotting all this, we're going to realize the graph is going to look like that. Generally, you start putting the vertical asymptote. So the way you represent a vertical asymptote is we use this these like scattered dots. And then we know that the function is never going to touch that graph. And then second thing we plotted is the y-intercept, because you guys realize we found the y-intercept previously, which was negative 3 over 2. So this is actually, this point is actually 0 comma negative 3 over 2. We know that the function must cross the y-axis, so we need to make sure that our curve actually crosses the y-intercept like it did on the given graph. And then on the right hand side, we're going to make sure to the one thing I need to emphasize is that because this function had a horizontal asymptote at y equals 0, the x-axis is going to be, let me actually use dotted lines. So you guys realize this guy is my horizontal asymptote, so I have to emphasize that as well. So yeah, generally speaking, sketching rationals are very similar to polynomials. You just need to follow a couple of things and make sure to do those as given in this slide, where you need to simplify, you need to plot the y-intercept, find x-intercept, find vertical asymptotes, horizontal asymptotes, and then come up with test intervals using not only the zeros, but also the the zeros or the vertical asymptotes. So make sure to include vertical asymptotes for your table as well. So yeah, that's gonna be all, and I hope you enjoyed this